Good afternoon, everyone. Let's start. A quick question before I start. As I'm preparing for next week, how many of you have done solid state physics, like Kittle's book? One, two, I think that was okay. How many of you have done quantum mechanics? One, two, three, four. Okay. So I'm bringing this up right now because if I try to follow the book assumes that you have done those things before, and it goes deep into optical devices. If I start doing that, will I lose you, or should I start a little bit low and then go up?
We just started, then we'll see.
Then you'll see. Okay. So let's try it out then next week. We'll start with quantum mechanics, most probably next Wednesday's class. And if it is going too hard, let me know, and then I can try to go down. All right. So today, I wanted to start talking about modeling a semiconductor laser, and in order to understand what is happening inside a semiconductor laser, I want to first build a phenomenological model, and then we will go and calculate various terms with that model over time. So this whole idea of semiconductor lasers, actually lasers, started with Einstein's brilliance. He should have received a Nobel Prize for this too, which was, he thought of that there must be a stimulated emission. So over here I have, I've just taken two states, a lower state and a higher state. For semiconductors, the higher state would be the conduction band, and the lower state would be the valence band. And just try to phenomenologically look at what phenomena as optical carrier interactions can happen in a two-state system like this. So within the state, on the lower state, I could have n1 number of carriers. By carriers, it would be electrons, and n2 carriers on the top state, right? So let's just say that. Then the carriers which are on the top, if there is a vacancy on the bottom, so the solid is an electron, the one with no color inside, that's a hole, lack of an electron or a positive charge sitting there. So these electrons really don't want to sit at a higher state. They want to come down, especially if there is a vacancy, if there is a hole left in the bottom. So they can recombine. So then an electron from a higher state can go and jump down to the lower state. And in jumping down, the energy difference they have, that energy difference comes out as radiation, as light. This kind of a radiation is completely incoherent. By incoherence, it means that it's randomly happening. So there is no relationship between a photon coming at one time and a photon coming at another time. And it's the photon being emitted, that photon is also randomly moving around in all directions. Right? So it's not necessarily following one case. If I went and I looked at another time, a photon may be actually going up like that in space, or it could be going backwards in space, right? So it's completely incoherent in that sense. So not in same phase in time or space. Our light emitting diodes, incandescent bulbs, fluorescence emission, that is through spontaneous emission. So that is basically a carrier at a high state, an electron at a high state, falling down, and in falling down, it creates a spontaneous emission, just spontaneously emits a light. For our model, we're going to use a rate of spontaneous emission, and we're going to call it R spontaneous, the rate with which this emission is happening. How many carriers are doing it at one specific time, so that rate. Later on, as we will build quantum mechanics, we will try to figure out how to calculate these rates. But at least build. Let's see why we need them. Then there is absorption. So a photon comes in, there is an electron sitting below. That electron gets the energy of the photon, and the electron jumps up to the higher state. So it goes and fills a vacancy in the higher state, and light is absorbed. This photon is absorbed. If I have an energy difference between these two states, so I have, let's call this state E2, E1. Then the photon which is coming up, that photon energy, which is h mu, h is the Planck's constant, that has to be greater than the energy difference for between these two states. Right? That leads to a photodetector and a photodetection process for this linear behavior. So this energy of the photon, if the energy of the photon is greater than this band, the difference in the two energy states, then this photon can get absorbed, and in getting absorbed, it throws an electron to the higher state. Now that's only for linear absorption. There are other absorption processes too. There is something called two-photon absorption. In two-photon absorption, or TPA, two-photon absorption, you have two photons coming in. Their energy is actually less than E2 minus E1. But what happens is one photon kicks the electron up, and then the other photon hits it and kicks it up again. And thus, the electron is able to go jump up. So two photons, like one photon hits it, starts kicking the electron up. There is no state allowed between these two energy states. In normal case, it would just fall down and it will be heat. But in the other case, another photon comes and hits it and goes up. And you can think of that this probability is going to be very low, but it does happen. This is what Einstein predicted. And he was comparing it with Planck's blackbody radiation. And he predicted that without this process, we can't explain Planck's blackbody radiation. Planck's blackbody radiation meaning that every body is radiating a certain frequency of light dependent on the temperature of that. Right? That's how thermal cameras are working. That's how many of the infrared spectra works too. So Einstein basically said if this process had no, there was no experiment at that time which showed that this process should happen. But he said to explain Planck's blackbody radiation, this process should also happen, and this process is stimulated emission. So in stimulated emission, what happens is the electron is sitting up on the top state. It wants to go down, but another photon comes. It kind of stimulates the electron. You want to go down, so go down. You want to give the energy, go give the energy. But the photon you create, make it a copy of me. Make it exactly my copy. Right? So instead of randomly falling down, you fall down and then make a copy which is exactly like me. This stimulated emission, so this photon comes in. The photon comes in, that photon stimulates the electron to fall down and create an exact copy. Then these two photons can go and start stimulating other electrons on the top layer, on the higher energy state, and they will start to make copies too. So you can see with this way, gain can be created. Right? You start with a small amount of photons, these photons starts to stimulate the electrons, and suddenly you get a large number of the same copies of these photons. So a gain starts to happen. Optical power starts to grow, and this emission is a coherent emission. That basically means the photons are exact same copies. They share all the same quantum properties. Right? They are the same phase in time with the same frequency, exactly the same frequency, and they are. You can't tell the difference which was the stimulating photon and which was the generated photon. You just can't tell. They're twins of each other. So that is a stimulated emission. And in any optical process, you're going to have both these processes competing against each other, right? There are these photons. These photons also have a probability that they get absorbed by the electron sitting in the bottom, so that the electron goes up. So the gain effectively comes from the difference between the stimulated emission, the rate of stimulated emission, and the rate of spontaneous emission. Right? That's how the difference comes in. And we'll see how we can create that. Then there is non-radiative recombination, in which ultimately energy is being converted into heat. So there are two types of non-radiative recombinations. One recombination uses these traps. Whenever you make any semiconductor, there are going to be some defects in it. There are going to be some surface charges in it. There are going to be some crystalline effects inside that thing too. There are going to be some impurities present in a system, right? So due to this impurity, you start getting another energy state, and what happens is electron goes and gets into those traps, and thus is not available for radiative recombination. So no light comes out of it. Electron is just falling down the lattice or colliding with the lattice and losing its energy, ultimately as heat. So that is non-radiative recombination, one non-radiative recombination. And the other non-radiative recombination, which plays a very important role in lasers, is OJ recombination. In OJ recombination, this electron falls down to a vacant state, but instead of giving its energy to a photon and emit light, it actually gives its energy to another electron sitting next to it, and that electron then shoots up to even a higher energy state, and thus gets out of my energy band. So this is OJ recombination is a 3 carrier process. Spontaneous emission is a 2 carrier process. I need an electron on the top and a vacancy in the bottom for it to fall down. Stimulated emission is a 2 carrier process. Absorption is a 2 carrier process, right? I need an electron in one state and a vacancy in another state for it to be able to go there. OJ is this traps is a 1 carrier. This carrier is this electron is just going into some trap which we haven't really provided. We don't want it, but there are some traps which are available. OJ is a 3 carrier process. So 3 carriers have to be involved. 1 electron combines with a vacancy in the bottom, and that energy goes to a second electron. And it can also happen with the holes too. So hole combines, hole is like a balloon, wants to come up. So hole combines, gives its energy to the other hole, and the other hole goes down deeper into the valence band. Right? So it can happen in both cases also. So these are the various optical transitions, and over the next 5, 6 weeks or so, we will try to figure out how to understand these from the quantum mechanical point of view, right? Where these come from. Today, all I want to do is, if these exist, how would a laser behave? How can we build a laser? What would its properties be? Today, and maybe one lecture to next week. But so these kind of states are easy to create in gases or where atoms are not closely interacting with each other. If you look at gas lasers, this would be, gas lasers would be so much simpler to describe, because in gas lasers you have different different orbitals, spin orbitals, not spin, sorry, different orbitals of the electrons, and you're basically jumping from one orbital to the other, so you just have different energy states, right? You have very discrete different energy states in a gas laser. When we go to semiconductors is a solid. These atoms are connected together very, very densely. So these energy states they start to split off. Right? So you start to create a lot of energy states within the conduction band and a valence band. And we will see this, how we'll calculate that. That's why I was asking whether you've done solid state physics, because this is coming from solid state physics. And this is mainly coming because of the covalent bands. So I have, let's say, I have an atom and an atom. We start creating potential wells in these atoms, and then you are trying to put an electron in that atom, so that the electron is going to have some wave function. This wave function can coherently add together, so a symmetric addition between two things, or they can incoherently opposite add together, right? So they can be in constructive interference with each other, or they can be in destructive interference with each other when these atoms are closely packed together. So there is tunneling of electrons happening from one atom to the other, and they could do something like this or something like that, like the phase becomes different. The same way we were doing optical waveguides. If I have two optical waveguides, I have a waveguide here, and I have another waveguide here which is far off. They are nice simple modes. I start bringing this waveguide close together. These two modes can interact in phase, so you create a mode like that, or they can interact out of phase, so you create a mode like this. Right? This is 180-degree phase shift to that. Same thing is happening here also. So that means immediately an electron can now go into two energy states, so that one conduction band has gone and split into two for every electron. So suddenly all these electrons, these energy states start to split off a lot. It would look like this is going to be a major problem for us, that the number of interactions which have to happen would now suddenly blow up on us, right? Because an electron can go from a state here to a state here, or could go from a state here to a state here at another state. It could jump anywhere, and all those interactions can happen. But as we will see, according to Pauli's exclusion principle, there are certain quantum properties which have to be conserved. And we'll see, even though the splits are happening, the interactions are only happening virtually between two pairs. So maybe this would be able to interact with one pair, but may not be able to interact with one pair. The electron just cannot jump there, because otherwise quantum properties are not maintained. So we will see that hopefully in another 4 weeks or so. Alright, let's go back to Einstein's calculations. So these are from his paper, and let's see how he came up with this stimulated emission. So let's say you have these two carrier states, a conduction band and a valence band. I'm calling the top one E2 and bottom one E1. Then the rate of absorption, rate of spontaneous emission should really depend upon how many charges I have available in the higher state. Right? How many carriers I have available in the higher state. The more carriers there are, the chances are that they will fall down. So that rate will depend upon some constant A. It's called Einstein's A constant, and the charge value over there. The rate of absorption, that would depend upon how many carriers are in the bottom. Right? A photon has to be absorbed by the carrier, so it would depend upon N1, and it would also depend upon the photon density. How many photons are there at a specific frequency? Because, as I've said, there have to be certain quantum properties which have to be maintained too. So it also depends upon the energy density per unit angular frequency. So this is basically, rho omega is basically saying, I plot what the intensity looks like versus omega for that light source. If I integrate this, that would be the total power in the light source, right, over that whole omega. Because every light source, we said, has some length to it. So it's also going to depend upon that rho omega. The stimulated emission, that is going to depend upon N2, the number of charges which are available in my higher energy level, and also on the photon densities. Right? How many photons are there to stimulate these charges to fall down? Right? If there's no photon available, no stimulation emission is happening. If there are more photons available, the probability that this photon will go and excite a carrier and say, hey, make a copy for me, I'm hungry, make a copy for me, that becomes larger. Right? The probability increases. So this would also be related to that. Let's call this coefficient B12. I'm just using the term 12 because it is from state 1 to state 2, and the upper coefficient B21 because it's related from a carrier from state 2 to state 1. If I was writing a rate equation, how the number of carriers change in the top layer, in the top energy band, N2, how does that change over time? Then that would be related to the spontaneous emission. So any spontaneous emission is removing those carriers. So that would be minus A by N2. It will be related to, I think I have a typo here, it should be B21. This should be B21 and this should be B12. So just change that. Those two have been flipped. So it would depend upon spontaneous rate of stimulated emission. Both spontaneous emission and stimulated emission is reducing the carriers in the top layer, and absorption is adding carriers to the top layer. Right? It's taking carriers from the bottom energy state and adding it to the top layer. So that becomes your bottom. If I now go to thermal equilibrium meaning everything has been stabilized, so no carrier change is happening, all black body radiation, for example, then dN by dt is 0. And if you just do some algebraic manipulations, we can write the photon energy, the photon, not the energy, but the photon density with frequency in terms of our Einstein's coefficients and the number of states we have. So just simple algebraic manipulations here. Now Boltzmann's distribution says that in thermal equilibrium, the carriers are the number of carriers available are exponentially decaying as you go to higher energy states. Right? There are some constants and then they are exponentially decaying. But there is going to be more carriers at a lower energy state. As you increase the energy, the carriers are going to be exponentially reducing. So if I look at the number of carriers in energy state 1 divided by number of carriers in energy state 2, that would be basically related to this exponential behavior, E1 and E2, exponential behavior to E1 kBt minus E2 kBt. T is the temperature, then the lattice temperature. Higher the temperature, the more carriers can be put up, right? There is more thermal vibrations and there is a chance that the carrier can shoot up through thermal vibrations. And higher the energy, the chance is less that the carrier is sitting there. So that's the Boltzmann distribution. So if we look at this equation then simply turns out to be the energy difference divided by kBt. kBt is the Boltzmann's constant, an experimental constant determined for this distribution. And E2, E1 is basically your photon energy, which is h frequency or mu. This is frequency f. If I was writing it in terms of angular frequency, this becomes h bar omega. And h by 2 pi, we write it as h bar. For people who have h is Planck's constant, h by 2 bar is normalized Planck's constant. Right? So this basically becomes as E h bar omega kBt by t. So if we now write our system, then these equations simply become, just substituting now, you get this kind of a variation. And if we now compare this to Planck's black body radiation, which had already been discovered by that time, an experimental law, really. At that time it was experimental, now we can go and derive it. An experimental law, Planck's black body radiation says that light coming out of a body at a temperature T is given basically by this expression. And suddenly Einstein saw that if he put this stimulated emission, he is seeing this Planck's black body radiation come out of his expressions, under the condition that this coefficient for stimulated emission, the rate of stimulated emission, should be equal to the rate of absorption. That V21 should be equal to V12, right? If you just comparing these two, because in Planck's black body radiation, you basically have a term of 1 in front of your energy term. So under this condition, if the rate of absorption coefficient, the coefficient we put in front of the rate of absorption, if that was equal to the rate of stimulated emission, we are now able to explain Planck's black body radiation phenomenon. And in that condition, if we just take and divide the stimulated emission by the absorption, rate of absorption, that becomes N2 divided by N1. The number of states in the top divided by the number of electrons in higher energy state divided by number of electrons in low energy state. What does this tell you? This tells you that if I want my stimulated emission to become greater than my absorption, I need to increase the number of carriers in a higher state. I need to increase the number of electrons in E2 compared to in E1. That in thermal equilibrium that never happens. So I have to break thermal equilibrium. I have to go beyond thermal equilibrium, right? So I have to somehow be able to do that. This term, that N2 is greater than N1. This is known as population inversion. We have to invert these populations to be able to handle that. And if you look at our spontaneous emission coefficient, if you just now compare the rest terms over here, that should be equal to this term. So the spontaneous emission term should be equal to that, should be related to that. That's the rate with which the spontaneous emission would happen, multiplied by the number of carriers which are there in higher state. And now we get to another issue, that if we look at the rate of stimulated emission by, this is wrong, sorry, correct this, rate of spontaneous. So this is not absorption but rate of spontaneous emission. If you now look at rate of stimulated emission by rate of spontaneous emission, we get a term like that. And again, h bar omega is much larger than kBt. kBt is just the room temperature variations. It's a small, it's like almost a factor of 10 lower compared to anything we are working with, unless you're going into quantum cascade lasers. H bar omega is much larger than kBt. So the denominator is much greater than 1. So rate of spontaneous emission is much greater than rate of stimulated emission. So just population inversion alone will not help us. Population inversion is basically, with population inversion, we only overcome absorption, right? So the chances now are, if we have achieved population inversion, that the number of photons we generate is going to be greater than the number of photons which are going to be absorbed. And thus, I'm going to get a gain in my system. I'm going to get more photons out than I can put into that semiconductor. Right? that is all what population inversion achieves. But even in that case, the chances that a carrier is going to fall down and create a photon spontaneously in random way is much higher than a stimulated emission rate. So we have to add something else. Just by semiconductor itself, just by population itself, we are not going to be able to achieve a lasing phenomenon. And that's where the oscillator comes into picture. We have to somehow build an oscillator, and what we have to do is something like that. So we have to build some length. Let's say we start over here. There are some spontaneous emission being created. These photons are coming in different colors and different directions. These are moving forward and creating copies of themselves. They create more copies or less copies. And they move forward. Then we give a feedback that all these ones don't go back, only certain selected ones start to go back. The other ones, we say, we allow them to escape somehow. We don't feed them back into the system. So now I've created a reflection here, and some of that you can now immediately imagine that some of this would be lost because there is a waveguide created, and this may not be guided and will be just not. So the waveguide will allow me to start to focus more and more of these, the photons which are traveling nicely along z-axis. Chances are that I would be able to start to build up them faster than the photons which are traveling a lot more off-axis. They will most probably escape my waveguide and thus go away. And then I give feedback, and I give a feedback. So I start to take these photons of my type, the ones which I want, start to feed them back and act over this oscillator, start to build up on itself and overcome the spontaneous emission. So that's where that is an extra thing we need. So laser, as I was telling you, is a misnomer. That laser is light amplification by stimulated emission radiation. It's not a light amplification, it's a light oscillation. You need that oscillator. Without that oscillator, you're not going to get a laser. So these are the lessons we learned from Einstein. And Einstein just did it out of curiosity. Nobody had even thought of lasers at that time. Lasers were only thought of, that this is 1906, right? This is Einstein's peak time, when he was publishing Nobel Prize winning papers every few months. He should have gotten a Nobel Prize for this too. He got a Nobel Prize for photodetection. He didn't get a Nobel Prize for special relativity. He should have gotten one for that. We're still living we're still like finding it to be valid, right, with new experiments. And he should have gotten a third Nobel Prize for this. Because of the impact he had, nobody would have thought of this. There was nothing experimental which was trying to show us where this is going to be. So Einstein just did it as curiosity. Then in 1940s, a maser was created in RF, which was an oscillator. So it was basically an RF oscillator which was trying to increase the power for radar systems. It was called a maser. So then people started thinking, hey, we can probably use that idea to create lasers too, without realizing that it would be coherent. And then a Canadian created the first laser in, I think, 1957-58. He was from the university in Vancouver, not BC, but the other one, Simon Fraser. He was an undergrad from Simon Fraser, then he went to Stanford to do his PhD. Theodore Angel, I think. And he created the first laser, and his first laser was not published. His work was not published. He submitted it to Nature, they rejected it. He submitted it to one other journal, they rejected it, and it was just a curiosity. And then it got published in Physics Review Letters, which then became an important journal. For 10 years after he invented lasers was a solution looking for a problem. Nobody knew what to do with it. And now we can't imagine our lives without a laser. We interact with a laser almost every single day today, right? So it's a very interesting history there. So two things we have learned from Einstein: that we need this population inversion, that we need to somehow get out of thermal equilibrium. We need population inversion, and how it's easy to do population inversion in gas. I can go and pump the gas with another source of light, shoot a lot of electrons up, and then hopefully they fall down to the state I want them to be, right? So I can do that in gas. But how do we do that in semiconductors? How can I create population inversion in semiconductors? And then the other thing, we need to be able to create a mechanism which thresholds the spontaneous emission, which says spontaneous emission is not going to increase after this specific value. It just becomes a threshold value. It becomes, and then any other carriers we are adding on N2 states, those carriers are just going to stimulate the emission. Right? So these are the two things we have to be able to do. So let's start with the second thing, and I'll do a derivation now. Is this okay? So let's do a derivation. It's very, very straightforward, as we had done the Febvre-Perot. So I'm going to do a derivation for a Febvre-Perot laser or a cavity. So I have some semiconductor. Obviously there is a waveguide in it because I need to be able to guide that light, and thus there is a light which is going through that. I create two mirrors, R1 and R2. And R1 and R2, whenever I write small, so small r is for electric field, and big R is for power, and big R is square root of small r. So if I was writing the power, I have R2, which is square root of R2, and R1, which is square root of R. Let's say, so this particular, there is an optical mode. The active region where the gain is happening is only this part. This is my active region, where carriers and photons are interacting. And thus, I have, as we have seen, when I try to confine the optical mode, the photons are a naughty child. They don't like to be confined in a small area. They start to escape out, right? There is a lot of photons which are going to be traveling outside too. So there is going to be a confinement factor, right? So gamma is the amount of power within the active region. The same confinement factor we had defined in our waveguides before. And let's say this particular waveguide, this has a gain of G, which basically means that if only this active region was present, if I put T in and I went a certain distance, my T transmitted would be exponential Gz. How do we calculate G, what that G is? We'll go to quantum mechanics and semiconductor physics, and we'll figure that out, what these interactions are. But for the time being, let's assume that we have been able to create that stimulated. So G is going to be related to R stimulated minus R absorption, right? So related to that. Within this mode, my power of the mode, if I was now looking at the power in the mode, that would be the power at any z, that would be power I input in the mode, but only gamma of it is getting the gain, not everything is getting the gain, only the photons which are here can create stimulated emission. These photons are not creating stimulated emission. So only this much of the photons are interacting with the carriers and creating gain. So this becomes Gz. Then within this cavity I also put some loss, and this is known as internal loss alpha I. This loss could be happening because there are some defects in my laser. It could be happening because, as we will later see, we'll have to dope this laser with some carriers, and there could be some, as this power sitting here could now start to vibrate with those dopants and lose its energy. So there is some loss which is happening within this waveguide. So with these parameters, let's look at what would happen. Let's say I start from point 1 and I start with an electric field E1. Okay. Can I erase the rest? I start from point 1 and I create an electric field there. This now starts to travel forward. It reaches to, at 2, this electric field has gotten some gain, gamma G, let's say this is L, so Z is L, but this G is defined in power, this is electric field, so I have to divide it by 2, and it has some loss, alpha I L by 2. This is moved forward. All these terms are defined with respect to power, but the calculations are being done with respect to electric field. An electric field squared is power. So in exponential terms, the coefficients become half in electric field. So this becomes gamma GL by 2. That's how much it's gaining due to this active region, but it is losing something from the due to some absorptions which are happening outside that active region. But besides that, there is also the propagation. So it is J beta L. Right? Then this gets reflected, comes to 3, and at 3 what would happen? This becomes R1. That's it. It just gets reflected, whatever is the reflection coefficient, and multiply it by. Agreed? Then this starts to travel forward. It reaches point 4. What else has happened now? At point 4, it is R1, E1, that remains the same, but it has gone through this one more time. It had gone through this length L. Coming back, it has gone through this length L again. So this expression is going to be multiplied by a similar expression again. So this particular thing becomes gamma G minus alpha I L instead of 2. And it has again been phase delayed. It has to travel that distance, so this becomes minus 2J beta L. Right? Good so far? And now there is a reflection which has to happen over here, and it comes back to point 1. And if this is a resonator, I travel one path back and come back. For the resonator action to happen, this better become equal to E1. Right? Only and only then the resonator action will happen. And I want that resonator action to happen. I need these photons to go and build up on themselves, keep on building up on themselves, and start to grow as it goes through. So now I have this particular term should become equal to E1 for resonance to be It is exactly like the resonance we have on a string, right? It's exactly the same resonance we are creating here, exact same thing, but now we get a condition like this. So it's now telling you this has to be equal to 1, so this I can cancel out, and thus I have an equation which is R1, R2, E comma G minus alpha L, E minus J beta L is equal to 1. There is the real part to it, and there is an imaginary part. There's a complex part to it. Both of them have to be equal to 1 for this to be true, right? So that tells you R1, R2, E comma G minus alpha L has to be equal to 1, and E minus J beta L has to be equal to 1. If we take the natural log on it, you can write this as gamma G minus alpha L is ln of 1 by R1 R2. I just took this here before I took the log, natural log. Great, so far? And it's now telling me there is one condition which is required, which is gamma G has to be equal to, call it alpha or alpha I? Let's call it alpha I. Has to be equal to alpha I plus 1 by L ln of 1 by R1 R2. Normally we never write these in terms of electric field parameters. We always write it in terms of power parameters. So we can write this as 1 by square root of R1 R2. Since I have a log, I can easily take the square root out and just write it as 1 by 2L ln of 1 by R1 R2. This is one of the conditions I need to be able to achieve. That this is called threshold condition, threshold field. This particular one is internal loss. This particular term is called as mirror loss. Alpha n. Basically, if you notice, G and alpha I have been per unit length, right? GZ. So you multiply those two terms up, which gives you the ratio, e to the power. So G and alpha I are per unit length. The reflectivities, if I have whatever is not reflected, that photons are getting lost to. But those are important photons. Those are the photons which we will see outside. The laser, the light which is being emitted to laser is the light which has been lost to the inside threshold condition, to the inside cavity, right? So that looks like a loss to the cavity, that I am losing this energy to the outside world. What we have done, we have taken that loss and we have averaged it over the length. Instead of just, this loss is only happening, the mirror loss is only happening over these two terms, at these 2 points. At these 2 points, suddenly some power goes out and only certain power comes in. R power is reflected, R1 is reflected, 1 minus R1 is transmitted, and that is a lost power to the cavity. So what this mirror loss term has done is basically saying, yes, I have that loss, but because my gain and alpha internal are measured per unit length, let's take this loss and average it over the lengths we have. Right? So then I can, whichever length I put, I can easily account for these two terms. Now if we look at gamma G or G threshold, let's say this is omega of frequency and this is gamma G value. G we have said depends upon, is R stimulated minus R absorption. So it depends upon the number of carriers in N2, right? N2 minus N1 effective. Because absorption depends upon N1 and stimulated emission depends upon N2. So it is N2 minus N1 effective. So the more carriers I put on the top layer, the more population inversion I get, I should get higher gain. So again, if I now look at it, if I change the population carriers, I should see some gain which looks like that. If I increase the population carrier, I start seeing gain which goes something like this. Right? So this is as the N2 minus N1 increases. The number of carriers increases, I should get more gain. But gain is only created if my frequency is actually, we are wrong. The gain is only created if my frequency is larger than E2 minus E1. There is no gain created if my frequency is smaller than that. So suddenly I will have a large drop, which in lambda would be a longer lambda. Right? So beyond that, there is no gain being created. So that is your gain. Then you have an alpha I, and then you have this mirror. Let's say we have chosen some R1 and R2. This is a straight line with frequency. Nothing is changing here with frequency. So it's basically saying I have to have, put it here. So something like that. This becomes my alpha I plus alpha mirror. Once my gain has become greater than alpha I alpha mirror, then this resonating condition can start to occur. So that tells you, hey, if I've only put these many carriers, I am never going to have any lasing action. But if I somehow shoot above that, as I keep on increasing the carriers, once my gain goes above that, so if I go into this region, everywhere here the gain is above this region. So in these frequencies, I can possibly create a lasing action. Now there is another condition, this condition here, E minus J beta L has to be 1, which basically is cos 2 beta L has to be 1. And remember, this is exactly what we were doing on Monday as a February for a cavity in M pi. Right? So beta has to be M pi by L. And if you want to put this in wavelength, 2 pi by lambda, M pi by L, you see that your lambda is beta is M pi, 2 pi, so pi will cancel out, lambda is beta is 2 pi by lambda. 2 pi by, let me put it in frequency. Don't let me put here because. Okay, I forgot my thought. I forgot my thought last time. If I remember it, I will do it again. Sorry. So beta is M pi by L. But this is exactly the same conditions we had seen before. Right? So now it's telling you that only certain frequencies would be allowed. So this would be m, this would be m plus 1 if I'm plotting it with lambda, m plus 2, so forth and so on. Only certain frequencies would be allowed. So yes, over this whole frequency, gain has become larger than my loss, but in that region, only this frequency has jumped up, this frequency has jumped up, and maybe this frequency has jumped up. So these two may be the only ones which would be allowed, which would start to build up. Okay? Only both the conditions have to be met. Gain has to be met, and absorption has to be met. Sorry, gain has to be greater than the loss, and the round trip has to be 2 pi. It has to be constructive interference over a round trip. So both of them have to be created. The cos to beta L is 2 L pi, 2 beta L is L pi, beta is L pi by L. That is correct. How can we, and we will talk about this in detail later on, but the next question that now comes is how can we create a population inversion in a semiconductor material? So let's talk about that graphically without equations today, so that we can move with our phenomenological element, and then I will come back to the diagram. So I have two semiconductors. If the semiconductor is, so this is a semiconductor, let's just assume there are two states. If this is intrinsic, my Fermi energy level is somewhere in the middle, right? Right? Somewhere in the middle, right? Somewhere in the middle. Fermi energy level is where the population density is half. Probability of finding a population, of finding an electron is half. That case. Then if I dope it with n dopants which have excess electrons, this Fermi energy level starts to move up. Which basically tells you I put some excess electrons and those electrons are sitting here, so they can start to conduct. And if I put p dope, I put dopants which have extra holes in them, that means they are hungry for more electrons, so there is more holes now present in the bottom. This becomes p doped. If I take a semiconductor which is n doped and I take a semiconductor which is p doped, Fermi energy level is where the probability of finding the carrier is half. Those two have to be matched. Those two have to be the same. So if I now start to combine them together, these two Fermi energy levels have to arrange themselves. So how would I draw when I try to combine an n dope with a p dope? Let me put p dope here. I have p dope on this side, and I have n dopes on the other side. The two Fermi energy levels have to arrange themselves, and my n dope becomes like that. And thus I get a band bending effect. If I now start to basically try to send electrons this way through the n dope, connected to a source, a battery, and try to send the holes this way, right in this region, which is known as the depletion region, you can see that there are, right in this region where the electrons start to gather, holes start to gather, it looks like there is a population inversion being created. There is more electrons here than right at the bottom. In this case, here there are electrons present here, but every state below is filled too. All these states are filled, so these electrons have nowhere to go below. Over here, these holes are present, but there is, all the electrons have been pushed below. There is nothing, there is hardly any electron which is present here for it to come and fill this hole. So I combine them together, these electrons start to come into this point, that holes start to gather over here. Right around that region now it looks like hey, I can create some population inversion. But it is very, very inefficient. Right? It's a very, very small region. I can control that. So to create population inversion in semiconductors, we go through what is known as a double heterostructure. So we take the same idea of this, but I put two different semiconductors. I have one semiconductor where the conduction band is large. I take another semiconductor where the conduction band is small, and I sandwich it between the third semiconductor. This side I do p doped, this side I do n doped, and I don't touch this at all. This is intrinsic, just a semiconductor. But this semiconductor is a different semiconductor. I have to change this band gap. Now, when I start to apply voltage or current and connect them together, I suddenly create a situation like that. And n dot material, p dot material, I am sending holes through. Holes are like helium-filled balloons. They will start to climb up. The holes start to get over here. The electrons are coming from this side. Fermi energy level is here in that case. The electrons are coming from this side and they start to fall down. And now what I have created here, I've created some kind of a well. Electrons are falling from the top, holes are rising from the bottom. I've created population inversion in this region. Right? This is how we can create population inversion in a semiconductor material. So two different semiconductors with a sandwich being created, and this is known as a double heterostructure. Next week we will see the equations behind this, how we can calculate the various things. But that is a simulation of a simple double heterostructure with Fermi energy levels arranged, and then there is a voltage applied. To separate this Fermi energy level, I have to apply a certain voltage across to start to separate the Fermi energy levels. So this intrinsic, the valence band Fermi energy connects with the Fermi energy level of the p-type semiconductor. Over here, the conduction band matches, and then I have applied a voltage QV. The QV voltage is exactly equal to this difference. So I have to apply, so now it tells you I have to apply some voltage to this device too, a specific voltage. And that specific voltage is going to be the difference in this energy band over here. Now when I'm sending electrons, electrons can easily come over here. These electrons will tunnel through, just like the way we were talking about the Fabry-Pérot cavity. There are two mirrors, the mirrors are thin enough. These electrons would just tunnel through, these holes will tunnel through, they will start to gather over here. And in this region, I have created a population inversion. In this region, I can start calculating gain. Today, just phenomenological. As the course progresses, we will see how we can calculate these, put equations behind these phenomena. So for today, somehow we have created population inversion, somehow we have created gain. Now let's see what would happen in a semiconductor. And this is the best analogy I can find. It's filling a tank which is leaky with a tap which could be leaky. So, I mean, that's the best I can think of. I've not thought of any better analogy than this. So I have a tap. The tap is the current you're putting. So I have current I going through. The number of carriers are going to be I divided by Q. Q being the charge, the elemental charge of one electron, and V is the volume of the active region. So this is number of carriers I'm trying to put per unit volume of the active region, I, Q. But this tap has some leak in it. This tap is not going to be very efficient. Actually, today they are very efficient. This tap has some leak in it. So some of the carriers, as some of this water as it is falling down, that is dripping out of this tap a little bit. And that's leakage current. Of this total charge which I put, some of the charge is going to go into this tap over here, into this, not tap, no, sorry, into this reservoir over here. We define a very phenomenological term. It's called internal quantum efficiency, eta I. This term has been wrongly defined by almost everybody. Anybody who took 4-7, like any optoelectronics course in undergrad? You took that? That book has it so freaking wrong. That book has it like 1980s version of it. And Chuang's book, the older book has a 95 version of it. The newer book is correct. So finally Chuang got correct in 2009. Eta I, internal quantum efficiency, is simply how much of the total water I try to throw here, total number of carriers I try to throw at the terminal, out of those, how many reached my active region. That's it. What leaked on the way out. Then, as this water is flowing, this tank is a bit leaky. There is a leakage happening due to spontaneous emission. So this is, I'm trying to fill N2, right? I'm trying to fill the top here. There is a leakage happening due to spontaneous emission. There is a leakage which is happening due to non-radiative recombination. And the tap is also, the water is also spilling over. We go to Niagara, water falls down, there is a mist created. That mist is escaping the Niagara Gorge. Right? That is water, that is basically water which has collided with itself, and some of that water has gotten so high potential energy that it has actually gone higher than where it started from. Right? That is water which is getting water molecules which are getting energy from other water molecules. That leakage happens here too. So all this leakage, whether this leakage is here or this leakage is here, this is accounted for in eta I. This leakage, this particular electrons which are leaving, these are known as hot electrons. They have thermally collided with each other and gotten that thermal energy to escape my barriers. So I can't collect that. So this has escaped out. If I was calculating what eta I is in terms of these rates, eta I is basically the spontaneous emission, the non-radiative emission, and any stimulated emission which is happening. I haven't shown that here. Any stimulated emission which is happening, the sum of these rates divided by the sum of all other rates. Right? Non-radiative plus leakage, extra leakage term which has come in. So eta I is basically saying, of the total volume of water which you send at the beginning of the tap, how much was collected in that well which you created. In a modern day, semiconductor lasers, eta I is very, very high. When I started working in '96, eta I used to be about 90% internal quantum efficiencies. By the time I finished my PhD 4 years later, 2000, we had changed eta I from 90% to about 99%. So there was a rapid improvement which happened. Today, if you're getting eta I below 95%, you should be looking for some other job. Right? It means you haven't understood the semiconductor processing well. You can easily reduce these leakage terms today with proper dopings, with proper designs. So today, semiconductor lasers have eta I approaching 99%. There was a rapid improvement which happened from '96 to 2000. After that, we have hit a plateau. There's nothing to improve left to improve after that. All right. So this is my eta I. Then I can write a rate equation in carriers, and so I'm going right now below the threshold. So dN by dt, how much my carriers are changing in my second state, N2, higher state. That would be related to any carriers which I'm generating, and the only generation I have is the current I'm pumping in, eta I by QB, right? So that is that term. And anything which is recombining, whether it is recombining due to leakage, due to non-radiative recombination or due to radiative recombination, spontaneous or stimulated emission. So G-gen is simply carriers you're able to collect in the active region. Recombination are the rates of the spontaneous emission. Below threshold is a condition where gamma G threshold becomes alpha I plus alpha minor, right? That condition. Below that value, the stimulated emission is always going to be lower than spontaneous emission. You've already seen that. Not only lower, much lower, right? There was E1 by E to the power h bar omega kBT minus 1. That's a really large term. So it is always going to be much lower than the spontaneous emission which is coming out of this. We also define a term, it's called carrier lifetime. So carrier lifetime is basically, we have this active region, we filled it up with some number of carriers, we stopped the tap, and we are now seeing how soon would this active region deplete of its carriers. Right? There are leaks happening, how soon would it leak out of that carrier? So we filled it up, turn the tap off, turn the generation term off, how soon it would start leaking. And dN by dt, again, it is basically called as minus n by tau c. Again, it is like it's basically, if you look at how, experimentally look at how it's reducing, it's going exponentially, it's an exponential decay term. So this term basically says that the N carriers simply become whatever you started with and not, let's say, T minus T by tau C as the time decays. It's slowly decaying in that term. And this term is related to R spontaneous and R non-radiative. R spontaneous, we had said, so this is a little bit unfortunate, but let's live with it. Einstein defined R spontaneous rate to be defined with B, with A, we define it with B. And Einstein defined the stimulated and absorption to be with B, those we throw away. A is something else for us. So this particular term is spontaneous emission, right? Two carriers have to be involved. There has to be a carrier on the top. It has to have a vacancy in the bottom to fall for it. So this is also known as bimolecular recombination. N is the traps. How many carriers are going into the traps? And Cn cube, that's where Cn cube, change that. Cn cube is the OJ recombination. 3 carriers have to be involved, and thus Cn cube is the rate with which OJ recombination is happening. Electron is colliding with another electron and throwing that electron out, and just throwing it into a very high energy state. For semiconductor lasers, mostly today, B rate is roughly 10 minus 10 centimeter cube per second, approximately that. That's the value for it, experimentally measured. C depends a lot on the design of your active region. And you want to reduce the hot electron effect. So if you can somehow cool these electrons down, you can reduce your value of C. How you design your quantum well structures can affect C a little bit. A is due to how you grow your material. Are there any traps in it, non-impurities as you grow? How good your person is who takes your design and grows a semiconductor layer for you. How much time is it? Let me just finish this carrier rate equation quickly. So the carrier rate equation then becomes eta R by QB minus n tau by minus R stimulated. Right? Just putting those specific terms in this case. Should we stop? Yeah, let's stop. I think it's a good point. The next is, let's stop here. and we will take the other rate equation, which is the photon rate equation, how photons are generated and how they propagate and interact with it in the next class. Any questions? This was not too heavy? Too heavy? This is good? Alright, so next class we will finish this phenomenological model and then build up on it to see how to calculate the various terms within this model. So in eta I in the previous book by Kasab, eta is defined as radiative divided by radiative plus non-radiative. So it puts spontaneous emission, it puts the OJ, it puts the non-radiative recombination as part of eta I. So that's the mistake there. And that leads to very strange results later on. It actually, no, eta I in my book is defined as stimulated divided by everything else. So even spontaneous is defined with eta in that old book from which you use in your lab. But eta I is simply the values you put here, how many reached that many. How many you stored in that? Like I have a water pipe, how much was I able to store in my tank?
I didn't remember the equation.
You didn't remember it? Okay. Sometimes I have to correct it, right? Because, I mean, that book has this kind of analysis, but the equations they get are so wrong, I don't even know why was it allowed to be published. Like, I even sent Kasapa an email saying, like, your derivation is totally wrong here. And it's not even close to being right. It's not even.
Did you respond?
You didn't respond.
But you fixed the book.
Which one?
But you fixed the book after.
I don't know. I don't think I haven't looked at the book because it's such a, it's a cookbook, not a textbook.
Don't publish a book, don't you know?
Yeah, that's why I don't publish it. I don't like publishing books because you never make any money out of it. You spend so much time. It's like if I have to give, I'll just give my knowledge freely out. Anyway, most of the students are downloading it from the internet, right? So you're working for free, and I don't like working for free. I don't to the core of my bones. I mean, I like working for free, but on my terms. So like, so my ECE 106, for example, all my notes are online and for free. Like I've written my own book, and it's for free for any student to use and others to use. So, but that's on my terms, right?
Sorry, I will